Okay, so welcome everyone to the Robotics Institute seminar. Today it is my great pleasure to welcome a fantastic speaker. We have here with us Dorsa Sadigh, unfortunately not in person with us, but at least virtually with us, joining us live from Stanford. Dorsa is an assistant professor in Stanford in computer science and electrical engineering, and she does very inspiring research at the intersection of robotics, learning, and control theory. And specifically, she's interested in developing algorithms for safe and adaptive human-robot and human-AI interaction. Dorsa did not have to move far. She received her doctoral degree in ECS from UC Berkeley. I think it's like a 30-minute ride. And she received also her bachelor's degree from UC Berkeley in 2017 and 2012, respectively. Dorsa had an exceptional career and received many awards, including important awards such as the Sloan Fellowship, the NSF Career Award, ONR Young Investigator Award, AFOSR Young Investigator Award, the Okawa Foundation Fellowship, MIT Technology Review 35 Award, and the IEEE Robotic and Automation Society Early Academic Career Award. But these awards speak not only to the exceptional person that she is, but also to the exceptional work that she does. Everything about her career is exceptional and non-traditional, including the talk today that will be about learning from non-traditional sources of data. Dorsa, we very much welcome you here, and we very much look forward to your talk.
Thank you so much. Thanks, Igor, for the kind introduction. So let me share my screen, just make sure everyone can see it. Everyone can see it? Yes. All right, perfect. Yeah, so thanks a lot for inviting me. Really excited to be here. And yeah, today I want to tell you guys a little bit about some of the recent work that we are doing in the lab in the space of learning from non-traditional sources of data. This is somewhat of a new talk, so I'm trying to get a sense of it. So there might be a little bit of hiccups. If there are hiccups, I apologize, but it is new material. So that part of it is exciting. So yeah, so in general, I'm pretty interested in building interactive agents, building robotics agents that can coordinate, collaborate, compete with people. And that a lot of times requires building good models of humans or building good models of how robots should act in the world based on interaction data or based on human data. And then that is kind of a space that I would like to talk a little bit about today. And let me just motivate the problem by a particular application that we have been thinking about for the past couple of years. And this is the application of assistive feeding. So this is a problem that I'm very excited about because I think it's a very difficult robotics problem, like picking up various types of food and dealing with deformable objects is just difficult. But also it's an interesting interaction problem because you got to pick up food and bring it to a person's mouth and transfer it in a safe and comfortable way. We actually have an ICRA paper on this year that's trying to take an attempt to this very difficult problem of assistive feeding. So let's look at a baseline of how this assistive feeding works. So this is a baseline model trying to use a fixed pose policy, going to a fixed pose, and trying to bring this carrot to a person's mouth. And as you can see, this doesn't seem very comfortable. I'm happy I'm not that user sitting there. And in general, this ends up being a particularly difficult problem. How can we transfer food in a way that is safe and comfortable tends to be pretty challenging. So at this point, this was again a year ago, we were thinking, okay, how can we solve this problem? Why is this difficult? And one idea is that maybe we can throw machine learning at this, right? Machine learning has solved everything. Maybe we can try to bring ideas from machine learning and see if that can address this problem. But that tends to be actually pretty difficult because if you think about this task of assistive feeding, I actually don't have good simulators of a person's mouth or these various types of food items that I'd like to transfer. So in those settings, if I don't have good simulators, I can't generate lots of data in simulation. So I kind of need to rely on real. And in the real setting, I cannot run reinforcement learning. This is a safety critical setting. I don't think we want to hit the food to a person's nose and get negative rewards. I don't think that is feasible here. So using just reinforcement learning out of the box doesn't really make sense. And then the other option is to try to learn from actual expert data, collect expert demonstrations, and maybe try to basically learn from expert demonstrations. But that also tends to be pretty limiting because we don't have that much expert demonstrators for various types of food items, for various types of mouth, and how we should go about feeding it. So I'm going to kind of like pause on this problem of assistive feeding. I'll come back to it at the end of the talk, but I was just trying to use it as a motivation of thinking about why it is difficult to use learning in these types of domains. And at this point, you might ask, well, how is it that children learn how to eat, right? Like, how do we learn like how to eat as a child? And one answer could be expert demonstrators, right? Like one answer could be that, well, we'll have a parent or someone, an adult, who teaches us how to pick up a piece of food by like demonstrating it or like moving our arms through kinesthetic teaching. And that tends to be a pretty useful type of data to rely on to be able to do this type of task. But the thing I would like to argue today in this talk is that that is not the only source of data. So in practice, I think we rely on many other sources of data, and we might not think about them, but they definitely exist, and they teach us quite a bit when we are thinking about doing these various types of tasks. So for example, when we are thinking about like feeding ourselves, one source of data could be unstructured play, right? Like as a child, we might play with our food, and that play with our food tells us quite a bit about the dynamics of the food and the state space, and gives us quite a bit of knowledge about the environment in general. And that's pretty powerful and important. And expert demonstration, just relying on expert demonstrations, is just not going to give us the same amount of coverage and the same amount of data. In addition to unstructured play, we might look at suboptimal agents, right? Like we might not always look at this perfect like expert and how this perfect expert like picks up food. We might look at other agents like kids our age and how they like pick up like a bite of spaghetti, and like that suboptimal behavior also like teaches us quite a bit in terms of what is a good bite and what is not a good bite. And similarly, like in addition to suboptimal agents, right, like we might also like think about comparisons, right? Like we might even like think about like comparison, pairwise comparison between what is a good, like nice, like bite of spaghetti versus slippery one. So we start making these sort of comparisons and rankings. And those are oftentimes also pretty informative when we are thinking about eating our food. So again, like going back to the setting of feeding, right? Like having a robot to feed a person, I don't think we should rely only on expert demonstrations, because expert demonstrations tend to be pretty limiting. And we kind of have already seen this in the space of robotics, right? Collecting expert demonstrations is oftentimes very difficult. Like we usually have very scarce amount of data, or like we end up having a fair amount of difficulty collecting various types of experts' behaviors. You might use various types of systems, like we might use VR, or we might use kinesthetic teaching, joysticks, various types of devices. But providing this data, collecting this data is time consuming. We end up collecting not very clean data, and we end up having a lot of difficulty when we are thinking about these types of tasks. And one could say, well, maybe we should just collect large amount of data from other sources, like from like the agents, like the different morphologies, other robots in simulation, and so on. I agree that's a good idea, but still there's quite a bit of domain gap when you're thinking about like a robot with a different morphology or looking at videos and so on. And that tends to be pretty difficult too. So in practice, there are many other sources of data that we can actually like use and tap into. And what I want to do in this talk is to tell you a little bit about some of our recent work where we are trying to go beyond expert demonstrations. So what I'd like to talk a little bit about today is how we can tap into unstructured play and learn from play data, and what are some of the challenges there. Then I want to switch topics and talk a little bit about learning from suboptimal demonstrations. And then at the end, if I have time, I will talk a little bit about comparisons and how we can learn from pairwise comparisons and rankings. And this is an area that we have done quite a bit of work around it in the past couple of years. So I will probably keep this one short and focus mostly on kind of like these two new sources of data, play and suboptimal demonstrations. I'd like to also emphasize that there are many other sources of data that I'm not talking about in this talk. So one could try to tap into videos or language data, or offline or online videos and language, as well as things of the form of physical corrections and physical interactions. And these are areas that we're actively looking at. But again, I'm not talking about any of that work in this talk. All right, so let's just get into it. So I'm going to start thinking about learning from play. So why do we care about learning from play? So the reason we care about that is oftentimes we would like to learn generalizable multitask policies based on these human demonstrations. And as I was arguing, human demonstrations are pretty difficult to collect. For example, like imagine that you want to learn a multitask policy that can do various types of things, like pushing an object to the right or forward or lifting it onto a platform. And for each one of these tasks, like pushing right, pushing forward, lifting, we need to collect some amount of data, right? Like if I want to do learning from demonstration, I actually need to have data for all of these different types of tasks. And that tends to be not very scalable, right? Like that ends up, like in general, like doing these type of data collections is expensive to design and expensive to collect. And what is the reason? Well, the reason is for me to be able to do any of these tasks, I need to have a rigid task specification. I need to have a reward function, and potentially based on that reward function, I need to come up with a reinforcement learning agent that can generate lots of data of pushing right and pushing forward and lifting. That is one way of me collecting data. Another way is just to get people to push right, push forward, and lift, but that is also like limiting in general. And then in addition to that, right, like if in the real world, right, if I get the agent to push the item to the right, then the item is now to the right, and I actually need to reset after each one of these demonstrations, and resetting tends to be pretty expensive. So as you might have seen, like in works that try to do these types of data collections, there's often a second robot that resets the environment for the first robot, because like in general, resets tends to be pretty challenging. So I'd like to argue that like collecting these types of data, it's not scalable and it's expensive to design and to collect. And in addition to that, it also has quite a bit of generalization issues. It's hard to generalize these policies. And oftentimes the reason for that is if you consider each one of these tasks, there's a start and goal state that is predefined. And our data is pretty limited to those particular state action coverage that we have seen in each one of these tasks. And that tends to be not very generalizable and fairly limiting. So instead of looking at expert demonstrations, one other source of data that's kind of useful is human play. So what is human play, or play data in general? Well, human play is unstructured, undirected multitask demonstrations where you kind of like act in the world, like move objects around and continue from wherever you have left off and continue with your play data. And then why is play data useful? Well, the reason play data is useful is first off, it is very cheap to collect. And that kind of addresses the scalability issue. There doesn't need to be any task specifications. We don't need to run any reinforcement learning policies that could actually do each one of the tasks very well. We could do whatever we want in the environment. It doesn't need to be perfect. And then it's reset free, right? Like we don't need to reset at all, right? Like we can just continue from wherever we have left off and continue with this very long string of play data, which is kind of messy, but like it's a long string of like moving objects around and picking items and putting them on platforms and so on. So it tends to be fairly cheap to collect. And in addition to that, it does have quite a bit of broad state action coverage, broad state action and goal coverage. And that could potentially address this generalizability issue that we have been talking about. Like imitation data, it only sees like the particular state and actions that are required for that particular task. But with play data, we can have a much wider coverage of the data. And it can, in some sense, access to these human priors on goals and behaviors, provide us these human priors that exist about the environment, about the goals, and how we should do various types of tasks, which tends to be pretty useful. So play data has been kind of used over the past couple of years. There was this Coral 2020 paper by Corey Lynch and others where they demonstrated one could try to use play data. And they actually have this figure in that work where they look at kind of like coverage, state coverage. And then if you think this plot, what it is showing is in blue, it's showing the coverage with play data versus coverage using expert demonstrations or coverage when you're just using random actions. And as you can see, the coverage of play data, again, is much larger than any other one of these other sources of data. And if you look at this like over 8 hours, as opposed to like 1.5 hours, like you start just seeing a larger, more dramatic difference. So this kind of like brings us to this hypothesis that if you're learning imitation policies from this play data, they're going to be more robust at test time. And one interesting point from this plot is that this is, again, much better than just random actions. Play is not randomly moving around in the environment. Play actually has a lot of structure. It does have quite a bit of information about the human priors and so on. So it's not random actions. It's actually like having much higher coverage beyond random actions. And that tends to give us policies that are potentially more robust at test time. All right, so now that I've motivated like why we need to learn from play, or why it is actually at least like useful to learn from play, what I'd like to do is I'd like to talk a little bit about how we can learn from play data, or how prior work have kind of addressed this. So this Coral 20 paper, what it was doing was it was basically thinking about this long sequence of play data, and it was basically trying to extract a particular like sequence from this play data and learn plans that kind of represent these random sequences from play. So in practice, right, like play is this long sequence of data. What they were doing was they were picking a two-second horizon window, let's call that tau, and then they were basically trying to learn some representation of the sequence. Let's call that a plan. That's a latent plan. So they were trying to learn these latent plans from these random sequences of data from play. Okay? And that kind of worked okay. So basically, like you take this sequence has a start condition as you're getting towards the object, and maybe has some final condition. It's not necessarily the final goal, but because you're picking a random sequence, but like at the end of like this sequence, maybe the object has moved and got to like a particular location. So OH here is representing the object's location at the end of this tau sequence. And what they were doing was basically they were trying to learn these latent plans from these random sequences. But there is a problem with this work. And I would argue that the key problem with this work is picking these random sequences, right? Like basically the idea is play is so long and has so much information. Let's just pick a random short fixed horizon window of 1 to 2 seconds. And maybe that 1 to 2 seconds is sufficient for capturing a plan. And sure, in practice and expectation, it is sufficient for some tasks, but it is not very like it's not a very informative way of picking that horizon. It is kind of like a random fixed horizon window, and they're using that fixed horizon window to learn these latent plans. So why is that a bad thing? So let me talk a little bit about why picking these short fixed horizon windows is a bad thing. And these are very natural things that I'm sure like you guys also think about, like picking random 1 to 2 seconds of window from a long sequence of play is probably not that informative depending on the scenario that you're in. So the first issue is that this horizon length that we are picking, 1 to 2 seconds, it tends to be kind of task specific, right? Like, and there is a trade-off when you're choosing this horizon. So for example, you might decide to choose longer horizons. Maybe you have a complex trajectory that does a detour and then continues, right? So that is the longer trajectory, longer horizon. But the problem with longer horizons is that if you're picking these longer horizons, sure, they are going to capture more complex goals, but learning from them tends to be pretty difficult in test time. Because in test time, you're trying to like match these plans as closely as possible. So if you have a much more complicated plan, in test time, it is really difficult to try to match that and actually like use those plans. Similarly, if you pick a shorter horizon, well, we kind of like know what the issue there would be, right? Like if you pick a shorter horizon, then we might end up in states that are out of distribution in test time, and it doesn't really capture the complex behaviors that we end up seeing. So in practice, this horizon length, right, it really depends on what the task is and what is the task at hand and what type of a horizon, what length of a horizon does it require. If you pick a horizon that's too long, the plans tend to be harder to predict at test time. We can't really match these plans that you're trying to train and learn during training. And then if you pick a horizon that's too short, then test time, like we might fall into out of distribution states in test time, which is not that ideal. So the first issue is 1 to 2 seconds fixed window, not a great idea, right? Like we might end up with horizon length that is fixed, but that should be really task specific. The second issue, building along like the same lines, is that like if I'm picking a fixed horizon window, I might end up associating wrong goals with these fixed horizons. Like imagine that you have a setting where you're starting with a robot moving towards your object, and you pick your 2 second window. And during your 2 second window, all your robot has done is getting closer to the object, but the object hasn't moved at all, right? Like the object hasn't done anything. The object has not like shifted in any ways. right? So if I'm picking a horizon that is too short here, right? Like I end up with goals that are not informative, especially if my goals are in object states, right? Like the true goal is much later. The true goal is when you've actually moved the object and the object had ended up in a new location. And you kind of want to associate this original trajectory that you have seen for that particular goal, but that goal doesn't show up in your window. So you end up with these uninformative end states that are not telling you what the true goal should be. Similarly, right, like you might end up with a too long of a window, which might have overlapping tasks, right? Like you might pick a window, your 2-second window might be this full thing where you start the task, you move an object, and then you kind of initiate your next task. Maybe you lift an object and put it on the platform. And this 2-second window has like 2 tasks within it. And if you consider this OH, this final object location is what you're going to consider when you're trying to learn from play data, but the true goal was much earlier, and we've kind of like missed that. So the second issue, right, is that when you're picking these fixed horizon windows, you might end up associating wrong goals with these fixed horizons. We might end up with uninformative goals at the end of the window, or we might end up having multiple tasks, and these task switchings could also cause a lot of issues. And then the final issue that I want to emphasize when you're picking fixed horizons is that if you're picking a fixed horizon, some fixed horizons are more critical than others, and we should actually like think about that. For example, if you're interacting with the object, right, your fixed horizon 2-second window corresponds to you moving an object. That seems to me more informative than maybe the retreating motion of the robot, like leaving the object and moving back, right? So some of these fixed horizons, again, are more critical for like their effects on the environment compared to some others, maybe that are not that critical in terms of like what has happened in terms of the goals in the environment. So random sequence sampling here is going to basically treat both of these sequences like equally because they're just random sequences of like 2-second windows from this data set. Okay, so just to summarize, right, like what prior work does when you're thinking about learning from play, what they do is they pick this fixed horizon and they try to learn a plan from this fixed horizon. And fixed horizon has a number of issues, right? Like horizon length should actually be task specific. You might end up associating wrong goals if you're picking these fixed horizons. And criticality of fixed horizons like are different between one horizon versus another, like the retreating motion versus getting to the object. So the key idea that we have here when we're trying to learn from play data is that we're viewing play data as object interactions. So the key idea here is actually very simple. So what we are proposing here is that you can still learn from play data. You should still go ahead and learn those plans, but you should think of play as these back-to-back environment interactions, and you should segment your play data based on those environment interactions. So for example, going back to my long sequence of play data, for like at some point during that play data, I have a pre-interaction phase where I try to like move towards my object. I have an interaction phase where I actually end up moving the object, like interacting with the object, making contact and moving the object closer to the platform. And then I have a post-interaction phase where maybe I retreat and like move back. And this post-interaction phase, one can really think of it as a pre-interaction for the next play data. Because again, remember, this is a long sequence of play data. I'm not resetting. I'm just continuing from this post-interaction to the next interaction. So one could really think of this as pre-interaction for the next phase. Okay. So what happens here is that what we're proposing is we should segment play based on when we make contact and what type of object interactions we have with the environment. And if we do that, then we can sample more informative and accurate goals. Like we're not like dealing with these random sequences where it's not even clear where the goal falls under. You're actually sampling like sequences that kind of like have goals at the end of their sequence. Like we are sampling from the interaction phase where we are thinking about object interactions as the informative thing that the plan from play should really capture. And what that does is it ends up biasing the latent space to model interactions rather than modeling random sequences. So again, very simple idea, but it's actually very powerful to use this very simple idea in this learning from play kind of paradigm. So the paradigm, like we're calling this PLATO, predicting latent affordances through object-centric play. And what this paradigm does is it basically segments the data into pre-interaction, interaction phase, post-interaction. It tries to sample a goal state from the post-interaction phase. right? So post-interaction, you can even imagine that even gravity acting on the object, or maybe the object sliding, and like that is where the post-interaction happens. So we look at where the object has ended up, like in this post-interaction, we sample that goal. And then what we do is we take the interaction phase and we try to encode that interaction phase into a latent plan, as opposed to encoding the full thing into a latent plan. So we encode that into a latent plan. I'm calling this an affordance, really. Like we're learning affordances when we are picking the interaction phase and trying to encode that. And at the end of the day, what we would like to do is we would like to learn a policy that is conditioned on our state, on this affordance that we are capturing, as well as the goal that is coming from the post-interaction phase. So PLATO has kind of like three components: sampling the goal, encoding the interaction into a latent plan, and then learning a policy that is conditioned on the latent plan and goal. But again, the latent plan is just coming from the interaction phase, from this more smart way of segmenting the data. All right, so why am I saying, well, this is learning affordances? Because if you think about an affordance, what is an affordance? Affordance is a property of an object that defines how it can be used. For example, an object being pushed. And what this Z is really capturing is that object being pushed. It is really capturing object interactions and the causal relationship between them, and what is the effect of like me acting in the world on the object. So what we do is, in training, we are going to take a trajectory that is coming only from the interaction phase. We are encoding that into a latent dimension, low dimensional plan. Let's call that Z. And this Z is going to capture things like, it actually starts having meanings. It's going to capture things of the form of pushing or lifting. And basically this kind of like biases the latent space to model these types of affordances. And then similarly, during training, what we do is we take our O1, like where our object starts with, and then the goal state that is coming from the post-interaction phase, and we try to pass those into another encoder that is trying to match this E as closely as possible. So in training, we're basically going to have a KL loss that is trying to match this encoder as closely as possible. Why are we doing that? Because in test time, I don't have an interaction. I don't have play data anymore. At test time, I just have a state that I'm starting from, and I have a goal that I'm trying to reach. So at test time, I would like to use this E prime, right? Like at test time, I would like to have an encoder that just gets the initial state, gets the goal, and is able to do various types of tasks, like performing a policy. So what I'm doing is I'm basically trying to find this E prime that is matching E as closely as possible, that is being learned from the play data. So I'm trying to make sure that this Z and Z prime are close through a KL loss. In addition to that, there's a second loss function that we're using here. And that second loss function is trying to like introduce our policy and learn our policy. So how do we do that? Well, once we get this latent plan, this is Z, these affordances, what we can do is we can pass that to a decoder. So this is kind of an encoder-decoder architecture. And we can pass that through a decoder that's trying to reconstruct an action that is as closely as possible to what we have seen in our play data. So, and in test time, again, we use the policy and we use E prime. So in training, I have three neural nets here, right? Like I have my encoder, I have a decoder for that encoder that's trying to optimize for reconstruction loss. And I have another network that is trying to match my encoder as closely as possible using a KL loss. In test time, I only have E prime and pi, and that is how I'm acting at test time. Okay. All right, so that's kind of the key idea of what is going on here. Okay, so let's see how that works in practice. So again, key idea was just segment your data, segment your play data based on when you're making contact and based on when object interactions are actually happening. And I was arguing that this is a very simple idea, but it actually has significant effects when we are thinking about learning from play. So we've demonstrated this work across a few different simple domains, but they're actually not that simple. They're more abstract, but they're actually quite difficult primitives in these domains. So we have a kind of like a 2D environment where we have a number of primitives like pushing an object, pulling an object, lifting an object, tipping it over. And side rotate, which is kind of interesting because you go and pick it up from the side and then rotate it. One could think of this as like opening a doorknob, like kind of interaction. We have looked at both machine-generated play, scripted play, and we have also looked at actual human play data. And we have also looked at a number of varying these primitives in terms of randomizing the block size and masses and positions. That is why I'm saying these primitives are actually fairly difficult, because they have quite a bit of generalization across things like block size and masses and positions. And these types of rotations tend to be fairly difficult too. So the comparisons here is with the PLATO work, which just takes a fixed horizon window, as well as using a goal conditioned behavior cloning policy on the play data. And what we see here is that PLATO actually outperforms the baselines on all of the primitives when we are using scripted data. And similar thing is true when we are using actual human data. So the bottom part of this table is when we are using human data. And it actually performs well on some of the more complex primitives. So like if you consider like some of these more complex primitives like side rotate, we see a much higher success rate, like 73%, compared to, let's say, using the PLATO approach, which only like gives 29% success. And one interesting point here is that dealing with human data tends to be a lot more difficult. And I kind of want to make a point out of this, because when we're working on this project, we worked with scripted data throughout, and we got these results and we were very happy about it. And we thought, okay, we'll just go collect human data and everything will be fine. And when we just collected human data, nothing was very fine. And we actually needed to make quite a bit of like hyperparameter tuning and changing part of the architecture to make sure that PLATO works well. And like all the other algorithms also like perform like reasonably when we are using human data. So here I'd argue that even like in these very simple settings of pushing an object or moving an object, human data tends to be a lot more variable than the machine generated data that we are dealing with. And in general, I think this is an important point, because as we are thinking about using large data sets, these data sets are coming from humans. And I feel like a lot of us, right, like tend to do various types of post-processing with this human data. And we don't even talk about that, but that is important, right? Like we remove zeros, we remove pauses, we try to make sure that we pick like clean human data. It is coming from that particular designer. But in practice, human data is a lot more variable. And in practice, if we want to use these large data sets, we need to be able to handle the variability of human data. And it was kind of like surprising that even in this very simple domain, we start seeing quite a bit of variability when we start using human data, and the performance drops like across all the methods when we're actually using human data. So I think that's a very interesting direction to work on in the future when we are thinking about like comparisons between human data versus machine generated data. But continuing on this play idea, like we also like experimented with 3D domains, again, using similar types of primitives like pushing and objects in various directions or rotating objects. And similar story is true here. So PLATO outperforms the other methods, again, significantly, just because the segmentation is better and is actually right. And it kind of like does it a lot more carefully. We also looked at, again, like another domain where we are moving an object to a platform. So we add kind of like this new primitive of lifting. And again, over lifting, we also start seeing like higher performance rates when we are thinking about lifting the object and so on, which is very interesting. So to summarize, so what I've talked about so far is this idea that we don't need to just look at expert demonstrations. There are other sources of data, and maybe we should spend time collecting these other sources of data, like play data, which has quite a bit of coverage, which has quite a bit of like allows for generalization. And not that we need to collect them. Like in addition to that, we need to be careful about how we handle them. And in this work, PLATO, what it does is it tries to segment the play data based on object interactions. And what it learns are these affordances that could potentially be useful for any goal condition planning down the line. So that's kind of the key idea of learning from play. All right. So now what I want to do in the next like 20 minutes is I want to kind of switch topics a little bit and talk about another potential source of data that can be pretty useful. And that is learning from agents with varying levels of expertise. So these are not demonstration data. They're not play data anymore. We're actually looking at full-on demonstrations, but they're coming from agents that maybe are not optimal. They're suboptimal in some sense. And I want to talk about an algorithm that tries to handle these suboptimal data. Okay. So the setting that we are in is that we are looking at offline methods. So you can think about it just traditional imitation learning, where you have some data from humans or machine generated data. And then the idea is that we have these offline data sets. We would like to go ahead and learn a policy for the robot. That's kind of generic imitation learning paradigm. And then in recent years, we have seen kind of offline RL versions of this, where we assume that we have some access to reward information, but it is offline. So then we kind of like look at this offline data set. The setting we are in is still in the imitation learning paradigm, where we assume that we don't have access to any reward information. And we also don't have access to environment dynamics. Like I can't do rollouts. I can't like go ahead and simulate and see what happens. We just have these offline data sets. That's all we have collected. And in addition to that, these offline data sets are from agents that have varying levels of expertise. Some of them are novice players and some of them are expert players. And we actually don't know if they're novice players or expert players. We also don't see their rewards. So it's not like we get a signal and based on that signal of reward, we are going to identify who is an expert and who is novice. And what we like to do is we like to do imitation learning from these suboptimal demonstrators. That is kind of the key setup that we are in. So let's think about kind of a very concrete example. So let's say that we can define an expertise here, and this expertise row, I'm going to just use it as a scalar for now. It can be more complicated than that, but for a second, let's imagine that we have an expertise row. It's a scalar, and that tells us if we have a novice player or an intermediate player or an expert player. Okay. And it captures how skilled someone is at a particular scenario. So in some sense, you can think of row as probability of succeeding. And if it is close to 0, then you can have a novice player. And if it is close to 1, you'll have an expert player. Okay. So as an example, let's think of classification. Let's say that we have a very simple setup where we want to identify the color of this shape, right? And if I have an expert player, the expert player is going to say red. And if I have, I don't know, novice player might think that the square is brown. Okay. And I have possible states of different shapes and different colors. And the correct action is to pick the color. That is the setting. That is the abstract setting that I want to show. Okay. All right. So let's look at this concrete example. So let's say that I have a number of states. I have agents with various levels of expertise. This is kind of like what they say. So if I have an agent with expertise level 0, they're going to get everything wrong. If I have an agent with expertise level 20%, so they're going to get like only one of them right. And similarly, this is going to go higher. And then finally, if I have an expert with expertise level of 1, this expert is going to get everything right. So now the question is, if I do have access to these rows, if I have access to these expertise levels, what should I do? What should be the policy that I would pick, like based on this data that I'm getting? One option is to just do majority vote, right? I have agents with varying levels of expertise. They're giving me like optimal action that they think is optimal. And what I can do is I can just take majority vote and go based on that. So it turns out that, well, not surprisingly, majority vote is not going to do so great, because majority vote doesn't consider expertise level. So for example, in this last row, majority vote is saying that the circle should be brown, but it's actually black. And the reason majority vote picks that is it's kind of like overly relying on these two agents who are novice players and they're not good at doing the task. So majority vote is just not going to like work well. So the other option is that I actually do like a weighted vote, right? So like, again, unsurprisingly, like a better approach to do is that instead of doing majority vote, if I have access to these row values, then I should basically downweight whatever this novice agent is telling me, because novice agent doesn't know anything. And then I should highly weight what the expert tells me. And if I actually do a weighted vote, I get the true answer, right? So the key insight is if I have access to the expertise level, I should do a weighted vote. And that weighted vote is going to give me the true actions and everything will be wonderful. But the setting I'm in is that I don't have access to these skills either. Like I actually don't know what the expertise are. Like I don't know what the rows are. Again, I don't have any reward signal to tell me what the rows are, but like I basically like need to, from this data set, I need to be able to identify what the rows are and go from there. So our key insight here is that maybe at the beginning, I don't have what the true rows are, what the expertise are, and maybe I'll just like uniformly like add them up and do majority vote. But when I have this data, when I have like what the majority vote has told me, what I can do is I can basically take this and go ahead and try to update my row values. So now using this column here, what I can do is I can go back and see how correct this particular player was and how correct this particular player was and so on. And that allows me to update the row values. And by iteratively updating the row values and as well as the policy, like we are basically able to learn a policy and expertise. Of course, this doesn't work all the time. And there's a good question of asking, like, what are the assumptions? Like, when does this work? And I'll get to that in a second. I think my PowerPoint crashed. Let me try to quit this and open it again. I think. Let me stop sharing for a second. One sec. I gotta force quit PowerPoint. Come on, force quit. I don't know why it does that. Let me see. So I'm opening my PowerPoint again. Okay, it's open. Let me share screen again. Okay, and let me get to the slide that I was at. Yeah, so I was on this slide. Okay, you guys can see everything, right? Okay,
yeah, looks good.
Okay. All right. So then, yeah. So as I was saying, right, like if I get like a policy that is not right, I can go ahead and update my row values based on that policy. And then I have a better estimate of what these agents are telling me based on these rows. I can do another weighted sum, and then I can go ahead and update my expertise again, and I can keep iterating, finally getting an expertise value that is closer to what it should be and a better policy. So one key insight here is that as we are doing this imitation learning policy, it should account for this varying levels of suboptimalities that we are seeing in large offline data sets. And the way we do that is by leveraging information about demonstrator identities. Like the fact that I know data is coming from a particular demonstrator, that allows me to like keep going back to that data and see if that agent was a novice player or was not a novice player. So the key reason that we are able to do this is that we're assuming data is coming from these different agents that are there with varying levels of expertise. And we are trying to identify those expertise levels as well as the policy like together. Okay. One other kind of like side note is that I've simplified things so much here. It's still like in the abstract world. You can imagine that these expertise to be state dependent, right? I might have an agent who is like really good at identifying the color when you're looking at squares, but terrible at it when you're looking at circles. So depending on what the state is, depending on like maybe the shape of the object, I might have agents that might have varying levels of expertise. So sometimes they have expertise level of 1, and sometimes they have expertise level of 0, depending on the state setting, the particular state that we are in. And in order to address that, we use these ideas of task embeddings. So maybe we have some tasks, and tasks have like, could be identifying the color, right? Like one task is identifying the color. So we can go from easy to hard. Let's say it's easier to identify the color of like red versus black. And then maybe another task is identifying the shape. Maybe it is easier to identify a circle as opposed to a square. And what we can do is we can basically come up with these task embeddings, these F functions parameterized by phi, that take a state and output a d-dimensional vector that give us kind of like these values, these different d tasks or skills that we can get. For example, like if you pick a red square, the task embedding over this particular state of red square in this particular case is going to be a 2-dimensional vector, because we have like 2 dimensions into our task. We have shape and color. And then in terms of color, right, like that is going to be a lower value because identifying the color of red square is not that hard, but it's going to be higher for shape because again, squares are harder. So very abstract, but basically like we can have another example here. Very abstractly, we can have like these task embeddings that take a state and output a d-dimensional vector that tells us what are the skills that we need to actually capture. Okay. So then how do we identify, so now let me get into some of the details of like the approach here. So how do we like identify these expertise based on the task embeddings? So we have the task embeddings. Again, these tell us how relevant each skill is. D-dimensional vector that takes a state, tells us how relevant each skill is. And then we're going to have this proficiency vector, let me call that omega. It's also d-dimensional. And it basically tells us this particular agent, how proficient someone is, or this particular agent is in each one of these D skills that we have talked about. Okay. And I've used rho as this like scalar so far, probability of succeeding at the task. But you can think of rho in some sense as an inner product of these two entities, the task embedding and how proficient you are in that particular task. So we take the inner product and we take a sigmoid on top to just like basically normalize it between 0 and 1. And what that tells us is that if my task embedding is correlated with my proficiency, then I'm going to get an agent who is very much an expert, because I'm going to get an inner product that's fairly high, and the sigmoid of that is going to be closer to 1, telling me that I'm dealing with an expert. And similarly, if they're not correlated, meaning that there are some tasks that I'm not very proficient at, this inner product is going to be highly negative, meaning that the sigmoid is going to be close to 0, and I end up with a novice player. So this is kind of what my rho is really capturing when we are including task embeddings. Okay. So then the question is, what is the policy of these agents? How are we modeling how these agents are acting? So the way we are modeling the policy of each agent is by saying that, well, these agents are going to take actions, the correct actions, with probability of rho, which is their expertise, the way I've defined expertise based on the task embedding and proficiency. And then when they take incorrect actions, the way they are taking incorrect actions is that they're uniformly bad across all these other bad actions. So they either are taking the optimal action with probability rho, and then when they're not taking the optimal action with probability rho, right, like what they're doing is they're uniformly taking a bad action. And that is an assumption that we are making here, right? Like you might be asking, when does this work? You never see any reward signals. Like, why in the world would this idea work? And this is one of the key assumptions that go into play. Like, we're not assuming adversarial agents, right? Like, we're assuming that other agents are uniformly bad. And because they're uniformly bad, like when you're seeing this large data set, you can actually identify the good behavior like among like all these other uniformly bad actions that we are seeing from
Dorsa, do you want to allow questions now? I think we have a question from
Okay.
Florian.
Yeah, sure. Yeah.
Hi, Dorsa.
Florian, please.
So I was wondering, what's the relationship between this type of model and the Boltzmann suboptimality model that people usually use to model irrational actors?
Yeah, that's a very good question. Yeah, so this is different from the Boltzmann one. Well, it's not, it's an instance of the Boltzmann one, because you can play around with the beta parameter with the Boltzmann model and actually get uniformly bad across all bad actions. So it is a simpler model than the Boltzmann rational model, I would say, because like I would say the Boltzmann rational model is trying to actually capture humans' real suboptimalities. This is kind of like a little bit of a simplistic model. But the simplistic model, the thing that it allows is it theoretically allows us to recover the optimal policy. That is why we are making this simplistic assumption. But it is true that, yeah, in reality, right, like people are not going to be suboptimal in this particular way. And I think that's a very interesting question to study. When we're using these more complicated rationality models, could we still recover the suboptimality? I think that would be very interesting. One point that I want to mention is, even though this is not true in reality, like I don't think in reality people are like uniformly bad across other actions. Like we've actually tried like using this algorithm on real data sets, and it outperforms like all the baselines, which is kind of nice. So even though this is a wrong assumption, in practice, like even if you're using real human data, using this idea could actually like provide like policies that are maybe not optimal, but like a lot better than what can one achieve with the baselines.
Got it. Thank you.
Yeah. All right. So just to continue on this, right? So now that we have this model, so this is the model that we are imposing on what the policy should be of what these suboptimal agents, again, might not be realistic. But once we impose this model, what we would like to do is we would like to learn an optimal or a policy close to optimal policy, right? Like we would like to learn pi theta that tries to learn this optimal policy pi star as closely as possible. And the way we are doing that is a very simple like likelihood estimation. So what we're trying to do is we have this data set, we're just optimizing the log likelihood of the data set based on this model that we have imposed on how the data set is, or how this data set actually looks like. So I've demonstrated a very simple version of this model that is kind of like looking at it in a discrete action setting. We have extended this to the continuous setting too, when we are using Gaussian mixture models as a way of capturing like the behavior in the continuous setting. I don't think I've included a slide on that, but basically like this type of model, right? Like there is an analog of that in the continuous domain. And once you have the model, you're optimizing like basically you're maximizing the log likelihood of your data based on that model that you're putting it here. And the things that we are optimizing, the decision variables here, are theta parameters, which are the parameters of your policy. So you're trying to learn your policy. And at the same time, you're trying to learn the task embeddings. So remember, like we had these task embedding fees, and we had these omegas, which were proficiency, and omega and phi together are telling us skills, are giving us skills. So I'm putting like phis and omegas like as separate variables here that we are optimizing using this framework. So the key idea, again, just summarize, is that given a mixture of demonstrators with varying levels of expertise, this algorithm, we're calling it ILEAD, imitation learning by estimating expertise of demonstrators. What ILEAD does is it basically maximizes joint likelihood of the policy, the best policy that you could do, and the expertise row, which remember is a function of task embeddings and proficiency. So let me just show you very briefly how things work on a number of experiments. I do want to maybe wrap up fairly quickly too. So the experiments that we have done is in 3 domains. So one is kind of a made up domain where we have this grid world environment with a number of different tasks, like reaching an empty square or avoiding lava or avoiding dynamic obstacles, or kind of like sparse reward tasks of unlocking a door and getting to the other location. So this is, again, like a synthetic environment. We're synthetically generating data. So of course we can have our assumptions being held like when we are generating this data. So this is a setting where we are saying, okay, our assumptions are being held. How does the algorithm perform? Then in the next 2 settings, one of them is this RoboMimic data set, which is from Stanford Vision Lab. And in this data set, they actually have human data at varying levels of proficiency. So they have data from, I think, 50 demonstrators. So 50 demonstrations from, 6 demonstrators. 2 of them are bad at doing a task, 2 of them are medium, and 2 of them are better at doing a task. And what we do is we just take all of this data without any of these labels, and we're trying to learn from these real data that's provided on these various types of robotics tasks in this RoboMimic data set. Again, simulation, but it does have these various true like suboptimalities of actual humans. And the final domain is a chess domain where we are looking at real data of people playing chess. So this is from this Leich's API. This is a existing data set of how people play chess. And we're basically using that data set that definitely has various levels of suboptimalities. So let me just briefly show like one example of results on each of these domains. So in the first domain, the interesting thing in the first domain is we actually have this notion of task embeddings, because we might have agents who are good at some tasks and not good at other tasks. So there is definitely like a multitask angle to this first domain, where maybe I have an agent who is an expert in the empty domain, but is not an expert in any of the other tasks. Or similarly, I have an agent who is an expert in lava domain, but not an expert in the other tasks. So the way visually I'm demonstrating these expertise levels is that this agent, empty expert, is expert in empty, but then gray shows that it doesn't have any expertise in the other domains, and so on. So, okay, so let's first look at a setup where everyone is an expert in everything. So everyone is like, this agent is an expert in everything, this agent's an expert in everything, and so on. So beta here is representing that expertise level. Beta 1 says that everyone's an expert in everything. What we are looking at is performance of ILEAD compared to behavioral cloning when we are using all of the demonstrations, or when we are using behavioral cloning on the best demonstrations. And of course, all of them are going to be fairly well when everyone's an expert in everything. But then we start reducing the expertise of these agents on the other tasks. So as beta is going closer to 0, you start seeing that the data is going to look more and more suboptimal. And that is when we start seeing ILEAD like eventually like outperforming all these other algorithms, especially when agents are not an expert in any of these other tasks, but have a particular like expertise level. So here are some rollouts of the behaviors from ILEAD and how they work. All right, so that's great. So like we are able to capture task embeddings, we are able to use the task embeddings and actually like work in this domain. But when we are using actual human data, so what would that look like? So I mentioned that there are different types of demonstrations in this RoboMimic data set. We kind of see similar results when we are using actual human data as well. And that was kind of nice because this is, again, a setting where our assumptions don't necessarily hold. And you're seeing like the behavior of ILEAD compared to BCRNN, and IRIS, which is an offline RL algorithm. This information, like this table, like these two are coming from a paper, the RoboMimic paper, and these are the baselines, the best baselines that they have used. And in their work, they were comparing offline RL versus BCRNN. Here we're demonstrating that ILEAD actually outperforms all of them because it actually like thinks about suboptimality of demonstrators. And it does not have access to reward, even though IRIS does have access to reward. We're not like seeing any of the reward. I will skip showing the rollouts of this, but yeah, again, basically the idea is that we could actually use real human data and kind of like identify their expertise level when we are looking at these real data sets. And the final domain is this chess domain. Again, this is like we are looking at a setting where there is 1 billion state in action. So there are like hundreds of thousands of players with different ratings of how good they are in these different types of tasks. We are only looking at chess end games. This is when there are only kings and pawns on the board. So this is kind of like the end games of chess. And we are looking at kind of like 10 million king pawn state actions from agents with varying levels of expertise. What we are demonstrating in this domain is if we can recover expertise. We're not recovering a policy here because it's incredibly difficult to recover a policy just by imitation without having access to any reward or any rules of the game or any of that. So all of the policies are just going to be bad if I try to learn a chess playing policy here. So what we're trying to do is we're trying to get data from agents with varying levels of expertise. These are expertise levels like that are ground truth expertise levels provided. And what we are showing is we can actually recover these expertise levels using this idea of iLead. So the skill that we are recovering is actually highly correlated with the expertise level of the data. So that is kind of nice. So, all right. So just to summarize, right, like I've been talking about this idea of iLead, like this idea of learning from suboptimal demonstrations based on having access to the demonstrator expertise, and I've shown that across a number of domains. Again, there are some limitations here. One limitation is that you're assuming non-adversarial suboptimality. There's a very particular type of suboptimality that we are assuming, which is this noised suboptimality. And that is the thing that actually allows us to provide guarantees that we will be kind of like getting the optimal policy. But that is a big assumption, one could say. And we're also assuming that we have a good state coverage. So we can actually we can actually recover good state expertise embeddings. Like one could be in a setting where it is actually pretty difficult to recover the state embeddings as well. But if we can recover state embeddings, and if we are under the setting where we have this particular type of noise model, then we can actually get the optimal policy. But if you don't have them, then like, yeah. And in some of the experiments, as I discussed, like we don't necessarily have these assumptions being held, but it kind of works well in practice, but it's just empirical. All right, so just to summarize, the key takeaways here is that data sets are often coming from multiple demonstrators with varying levels of expertise. And we should try to identify those expertise levels when we are trying to learn these better policies. And that can allow us to tap into this larger data set and not just rely on expert demonstrators, actually rely on suboptimal demonstrators that can learn from these varying levels of data. Let me just try to wrap up. So I'm not going to talk about learning from comparisons because we don't really have time for that. But that just very briefly, that's just another source of data, right? You could think about comparisons between two different behaviors, and humans have a much easier time giving that type of data. And we can be a lot more efficient in terms of coming up with active learning methods of actively generating queries to a person and trying to ask a person how to do this task. And one of my students, Erdem Biek, has been leading quite a bit of work in this domain. Here is just some results on that, where we are looking at active learning and trying to learn these nonlinear reward preferences of people when we are thinking about these walking gaits. So people have different types of gait preferences when they're walking, and we are actively querying people by these pairwise comparisons to actually learn what their preference model is. All right, so just to summarize, I've talked about the three different sources of data: play, suboptimal demonstrations, and comparisons. And all of them are really useful when you're thinking about learning robot policies. Just to go back to my feeding example, none of this is right now being used on the feeding project. It's much more difficult. And even if you tap into this type of data, I think it's pretty difficult to try to do anything using learning in the setting of feeding. Nonetheless, this is a very exciting problem. We're actively looking at bite acquisition and feeding. So how do we pick up food? Here are just some failure videos for you to enjoy. Really difficult to pick up various types of food with varying levels of deformability. Sometimes our fork breaks, sometimes the object slips, sometimes we've just smushed it so much that it's hard to pick it up. And then similarly, when we are thinking about the transfer inside of the mouth, that is also a whole beast on its own. So there we are not using, again, any learning. We have a force torque sensor, and based on that, we're trying to identify policies that can retrieve once they have transferred food inside of a person's mouth. But I would be excited to use these types of ideas in the feeding domain as well, in the future. And I think that would be an interesting domain to look at. So with that, I'd like to thank the group And I'd like to thank you guys for listening, and I can take any questions if there's time. I mean, I'm over.
Thanks so much. This has been really a fantastic talk. It's really inspiring. I particularly like the byte transfer video at the end. I can imagine how fun this must be, like doing this all the time. A few remarks about questions. For those of you who are in Zoom, you can write the questions into the chat. You can ask them also in video. For those who are on YouTube, you can also ask questions, and Kimberly will transfer these questions to us, and I will ask them for you. So please feel free to ask questions while you think about them. I will get started and ask maybe a few. So first of all, I really like this idea of modeling human expertise. It makes pretty much sense. And if you do learning from demonstration, there are, like, my impression is there are two aspects of it. On the one hand is the human expertise model, which may be varying between the demonstrations. But on the other hand, there is the world physics, which is always correct between demonstrations. Mm-hmm. So what are your thoughts? Is there a way to, on the one hand, make full use of learning the structure of the world, while at the same time decoupling this from the potentially terrible skill set of a human?
Yeah, that's a very good, so I think this direction is pretty interesting. I'm super excited about this direction in general. And I feel like there are a lot of like next questions and what could like try to like answer here. That's a very interesting point, right? Like, could we learn like specific like priors and information about the world from this data that is uniformly across like all these different data sets? And like for that, I'd like to like one connection to that is this idea of pre-training models. And I think that like type of work tries to address this. So this idea of building large foundation models in a similar way that GPT-3 exists for language. It would be interesting to think about an analog of that in robotics. I think those types of models, like the only thing that is really captured in pre-training should be these physical priors. And right now it is pretty black box. I think like adding a bit more model-based techniques to that could be interesting to think about, like, how are we going about learning these structures? But yeah, you're absolutely right. Like the variance between these different types of human data is like potentially there's suboptimality. And the common thing is potentially like the physics and priors that you need to have about the environment. And it would be interesting to capture that. I don't think there are too many works that are doing that today, but definitely like interesting direction to consider. One other point you mentioned is that the person's suboptimality changing over time, which is again a simplifying assumption that we made here. We assume that, oh, the demonstrator is just naive and always naive, or the demonstrator is an expert and is always expert, but that's not true in practice. People get better, people change, and one needs to consider that too.
Yeah. Another thing that I thought of was about the work that you did you did on playing. So what are your thoughts when you think about this play work? You had always this very, in some sense, atomic actions, like one object interaction. In certain types of play, we have more than one object interaction. So for example, when we build Legos, there is like an entire hierarchy of actions. Like, do you have any thoughts of how we could model such hierarchies?
Yeah, I think that that was one of the things that we, again, didn't cover in this work, but it is something that you're thinking about. So multi-object interactions is also definitely like an interesting point to try to capture. So here we are thinking about capturing affordances, but these affordances could be based on multiple objects interacting with each other and their causal relationships, right? Like a block, like hitting another block will have some sort of effect. And ideally, what we want these Z variables, these latent variables to capture is that interaction as well, that multi-object interaction as well. And then what we want to do is we want to find a policy that is conditioned on that type of interaction and is able to like produce that. We haven't looked at, like, it becomes like more difficult when you consider multi-agent interactions, but I think it would be interesting to take it there.
Okay, cool. Then I think we have a question from Florian, and Florian is asking, what are your thoughts on ensuring safety during the collection of play data? And I assume he means the real world play data.
Yeah, we haven't looked at real play data yet either. It's a very good question. I'm actually more concerned about safety for the feeding project right now, rather than the play data as much. But yeah, the way I think it is important. I think Sure Play is providing like more cheaper ways of collecting data because you don't have resets and you don't have all these other issues, but you still have like some safety measures that you need to like consider, like even like simpler things like hitting joint limits, or like, I don't know, pushing so much like into the space. So I think like with Play, maybe it's a little bit easier because you can define your workspace and you can define like kind of like a set of actions, like a limit for the set of actions, and let the robot just act in that environment. I think with some of the other domains like transfer of food to a person's mouth, that tends to be a lot harder. Yeah, like when do we know we are sure that this is fine to work with real people? Like my student the other day was saying, if I have the policy like running like 40 times perfectly, are we ready to try on real people? I'm like, I don't know what does it take for us to be ready for this is definitely like an issue that we are dealing with.
Yeah, definitely. Then there is a conference room question from the Vector conference room. So please feel free to ask directly.
Hello. Thank you for the great talk. I just had a question about the iLead part.
Yeah.
I was wondering if you could comment on the kind of average number of demonstrations you needed per demonstrator.
Yeah, that's a good question. Yeah. So there is kind of like the practically what did it need? And then there is kind of like theoretically like what you need. So the theoretical results are asymptotic. The theoretical results are, as you have like infinite data, you can recover the optimal policy. So that's kind of like on the theory side of it, like what you can get. In practice, it's actually not that much, right? Like in practice, if you think about the RoboMimic data set, that's only like 50 demonstrations, and we are getting success rate of like close to like 90% on complex tasks, like putting like a peg on like putting a ring on a peg, kind of a task. So in practice, it's not as bad, but it depends on, again, it depends on how much you're having, like your coverage is sufficient, coverage of state actions is sufficient for achieving the task and learning good task embeddings. So it varies and it ends up being task dependent, but in theory, a lot.
Okay, thanks. So I have one more question, if I may. I think we need after that to wrap up soon. But I remember on your Play work, you mentioned that it was so hard once you switched from the simulated data to real data. Can you comment to some of the problems that you were having and what you used to deal with these problems?
Yeah, we ended up like, again, playing around with hyperparameters, and we ended up having a much larger architecture, which was interesting because like you need to have a much more expressive model to be able to handle the variability of humans. I mean, which is kind of expected, but we weren't expecting to see this much variability on like a simple task of pushing an object where the data is just collected by like my graduate student. And he was like worried about even getting data from another graduate student who was involved in the project. He was like, not even like my own data, like even that is so much variable. And we keep seeing that across projects, like the fact that human data is so difficult to deal with, and like people don't, again, talk about it as much. They're like, oh, we'll clean it up, everything will be fine. So I think that is something we should think about, like the fact that there's so much variability, like how does that affect our algorithms? How does that affect our data collection? How does that affect our data augmentation? I think are all important problems to think about. But specifically what we did was much more expressive models to capture the variability and more data. Yeah.
More data seems to be like a very common recipe that helps in these cases. Okay, I think I see no further questions. So Dorsa, once again, thanks so much for this really amazing talk. We all of us really enjoyed it, and it was great having you here. And I hope one of the next time it will be also in person. So thanks again, and thanks everyone for attending, and hope to see all of you